All right, everyone, welcome. Thanks for your patience. I'm going to try to make up for it. So this is our last lecture on the Newton-Euler equations, and I'm going to give you an overview of how to use them and how to gain even more insight on its use. And I think that the one of the best ways of seeing this is first, I do a couple of conceptual problems that are relatively not straightforward, but that are quick, but that go to specific things that I tend to see that students miss. And then I'll try to do hopefully one or at least two of the full-size problems that are going to help you with your homework today. So we did something similar to this last class, but I think it's very important that we pay a lot of attention to this. So in here we have this homogeneous disk. And then what we need to find is which of the ones below are acceptable formulation of the Euler equation for relating our moments to the angular acceleration, right? So you remember the Euler equation is given by this equation, and it has these two terms on the right-hand side. One, it's the moment of inertia of the body times the angular acceleration. And the other one is the term that we need to avoid, essentially, right? We don't want to do more calculations than what we need to. But to do that, we need to make the right decision when we take, when we're going to take moments, right? And the right decision means that either we take moments about a fixed point, we take moments about the center of gravity, or one of these very special points where the acceleration and the relative position are oriented in the same direction, right? Like in the no-slip condition. So for this specific problem here, let's look at all the options, all right? So essentially the question requires that our choice of the point where we take moments eliminates this second term, right? So let's look at this. The answers are there. All right. So for the center of gravity, it's point G. So then the distance from where we take moments is G, right? So then the radius is 0, so it's a correct choice. Now, if we take the fixed point D, then the acceleration of this guy is 0, so then it's correct. Now, point O is a moving point. So then the acceleration is not 0. So then it won't be correct. And then point E, it's on the rim. It's also a moving point. So the acceleration won't be 0. So the fixed point and the center of gravity, as we have discussed, are the good choices, all right? So we need always to remember that. And then the other thing is that we need to be consistent. Whatever we choose for the point where we take moments is what we need to choose to put here, here, and here. Otherwise, for instance, if we say, okay, I take moments about O, but I calculate the moment of inertia about G, then that is not going to work out. So this is very important to remember. Is this clear for most of you, or yeah? Okay. Now, another common problem is when we're dealing with pulleys. So pulleys before, in chapters 1 to 4, we were treating them as ideal, right? They were not changing the tension. We would say the tension here and the tension here was equal. But that was only because we were saying that the pulley was ideal. So let me show to you what an ideal poly is by solving this problem. So in here we have a block that has been lifted, and it's been lifted with a decreasing speed, right? So the magnitude of the acceleration is, if the speed is decreasing, the acceleration is negative, okay? So the poly is now non-ideal, so we need to have open eyes now, because it's going to be different if we have an ideal poly from a non-ideal poly. And look at this, this is the key. It has mass. Before, ideal polys were massless. That was the property that made them ideal. No mass. So let's see what's going on with that. Okay, and then we're asked whether the tension in section C is larger than in section D, or they are equal, or they are, you know, one is smaller than the other. We need to find which one is greater, essentially. Okay, who wants to wager that tension is greater in C than in D? Okay, we don't have time for wagers, but let's see if you guys are correct. So we have that the acceleration of A is negative. Essentially, we need to find the tension in the cables, right? So it's a system that is composed by one body and two bodies, both of which have masses. And we need to find forces, right? The tension. So our strategy for a free body diagram is to see the system as a whole or break it up. We need to, which of the two? We need to break it up, okay? Break it up if you're looking for forces or accelerations. So we have a non-ideal poly, right? This non-ideal poly is going to have these forces, you know, mass, etc. Is going to have a tension applied over here, and is going to have tension TD applied over here. That's for the poly. Now for the block, it's going to have the tension up and the weight down. Now we need to take moments. So where do we take moments on the poly? About the center, right? We will not say that it's inhomogeneous, so center of gravity is at the center, and the center is also fixed. So that's an easy decision. So let's take moments. So this guy is giving a positive moment, Tc times r, and this guy is giving a negative moment, Td times r, and then this is equal to the angular acceleration times the moment of inertia about O. For the block, we take forces in the y direction, right? In the x direction is not moving. The block is not rotating, so I don't look for moments. So essentially it behaves like a particle. So we have negative mg plus positive Td. It's equals to 0, or what? Mass times acceleration, right? So I'm dotted every time I take off points, because one has a block and one assumes that the block is at equilibrium, right? Even so, you know, it's even explicitly we're told that it's not at equilibrium, that it's not at static equilibrium, I should say. It has acceleration. So don't forget that. Okay, so we have, you know, 1, 2, 3, 4 unknowns, 2 equations. So we need a bit of kinematics. Now, again, if for an ideal poly, this would be 0, and then the tensions would be equal. This is the origin of why the tension is changing, okay? The fact that that circle has, the poly has a mass now. Okay, so kinematics, what do we know? We know that this guy is negative, right? The acceleration of A by the problem statement. So if the acceleration of A is negative, what can we say about mass A? It is being lifted, all right? And if it's being lifted, then how must the wheel be rotating? Counterclockwise, right? So the angular velocity is positive. And then we do the common trick of saying, okay, we have a cable, the cable is inextensible, so the acceleration of this point and this point is the same, right? Remember that from chapter 1 and before. So we say the acceleration of point A on the pole is equal to the acceleration of block A. And then we use chapter 2 kinematics. It's a planar problem, so we can do this. And a little bit, okay, the center is fixed. And then a little bit more of algebra. We take those cross products, we assume the angular velocity be positive and let the equations tell us if it's true or not. This is K, and the distance between O and A is positive. Is there a problem? No? Okay. So then we have K cross I is J. So we get this, right? We get one term in the J direction, one term in the I direction. Now, what we know is that the acceleration of the block, it's the same as acceleration of that point on the pole, point A prime, but only in the Y direction. The X direction is not affecting the block, right? So we can say that the acceleration of A, it's equals to the component in the J direction of the acceleration of A prime. So it's this, alpha times R. And we know that A is negative because the velocity when it's been lifted, or the speed, it's been decreasing. So what does that mean? If A is negative, what do we know about the angular acceleration of the pole? Is negative also, right? So it's clockwise. So that means that when we go back to our equation 1, if we go back here, if this guy is negative, then which is greater than the other one? So let's write it again. TCR minus TVR, it's equals to this. But we know that this side is less than 0. How can this happen? Exactly. Tension C is smaller than tension B. Okay, so this is how we do it with equations. Is it clear? Yes? So the trick was, remembering the kinematics. But how can we know this in terms of, like, physically, very quickly? Well, this guy is pulling the whole thing. That force is pulling the whole thing. The reason why we use so F is pulling the whole thing. Now, if A was accelerating upwards, then F must be pulling the whole thing and also carrying the weight and compensating for the added positive acceleration. Does that make sense? Hence, the tension in C would be greater than the tension in D. Because when you're pulling, but you're decelerating, it means that the tension in D is, pushing against your force, right? And Tc and the force are equal. Those are equal. So then in that case, then Tc is smaller than Td, because Td is not only pulling up the weight, but it's also pushing against the force. Does this make physical sense? Now, if you want to be safe, use the equations. But I want to give you also the intuition. And I want to specifically give you to be on the lookout for non-ideal and ideal products, because it's going to happen in some problems, all right? Any questions? Okay, so this, I think it's two of the main points that we need to remember. I did actually make a lot of important points. Never forget the mass times acceleration term when you're looking at a block that is hanging, and then some kinematics that we did are also given in this problem. So let's go to page 305. So now we're going to do, this is probably one of the most important discussion sessions of the whole book. Because what you learn here for rigid bodies, you can use in, everything that needs to be dealt with something that it's not a particle, and any mechanical problem. This is what you do. Okay, so let's try to see this. Newton-Euler equations essentially are telling us the following. To know how a rigid body is moving, we need to calculate the summation of forces on the rigid body, and that it's equal to the mass times acceleration of the center of gravity. Extremely important, of the center of gravity, right? We cannot choose any other point for Newton's equation. And then Euler equation is giving us this equilibrium of moments acting on the body. And we know that we have some choices for the equilibrium of moments. The important thing is that we need to make sure that when we take those moments, they are taken about the same point. And the moment of inertia needs to be calculated about the same point, all right? And then if we want to make our life easy, we need to try to get rid of this term with the choices that we have spoken before already. Very important. Now, sign convention. You can choose whatever sign convention you want, and actually, not now, but maybe in future lectures, I'm going to make some choices that are not the normal one, in which we say up is positive, right is positive, and counterclockwise is positive. Now, for now, while you get a little bit more practice, I think that you should try to choose that one and be consistent. So sign convention is very important. We need to keep it. Otherwise, if we do, we break up our system and we use different sign conventions for different bodies, then we may get in trouble. Moment of inertia. Moment of inertia is a very, very important quantity, and we can calculate it about any point we want. It doesn't need to be even in a rigid body, but typically we calculate it about a point inside a rigid body. And what is very important to remember is that this is the effective inertia that the body presents or makes you feel when you try to push against it, to move it. And this effective inertia is always given by the center of gravity, by the moment of inertia calculated about the center of mass of the body. And if you calculate it about any other point that is not the center of mass of the body, you are adding inertia to it, okay? So if in a problem, somebody ever tells you, oh, in this point, the inertia is less than the inertia in the center of gravity, then you know it's wrong. It cannot happen. So taking moments or calculating the moment of inertia about a point that is not the center of gravity of the body increases the inertia. You will have greater inertia. So, here, if A is not G, then you're always adding IA is always greater than IG. It generates more inertia. And then this concept of radius of gyration. Essentially, the radius of gyration is telling you the following. If you have a body like this, you can convert it into, well, actually, we have it here. If you have a body like this that is rotating, or that you calculate moments about point A, this radius of gyration is essentially a distance, the square of which you multiply times the mass of your rigid body to give you the effective moment of inertia that you would feel. So in a way, it's like concentrating all the mass at a distance Ka from the point you're taking moments and putting all the mass of your rigid body here. So typically one does that because when you have a complex system, like my body, let's say, calculating the moment of inertia of my body is complicated. I have a horrible shape. It's not an easy integral to calculate. But I know my mass. I just put myself on some weight, and then if I put myself on this and start rotating, you know what is the axis of rotation, and you can put my mass there. So there are ways in which we can infer. Actually, this is done to be able to measure the moment of inertia of a particle indirectly. But in most problems, what we're going to do is the opposite. We're going to give you a rigid body that looks funny, and we're going to give you the radius of gyration. So for you, let's say in solving problems, you need to remember this formula, that the moment of inertia of that body is going to be K, and then you need to be careful that if we say radius of gyration about G or about O, then you need to calculate then your moments about that same point. So I really encourage you, you should do it. Please trust me, read those 8 points with care, take some notes, and this is going to clarify a lot everything that you need to know about rigid bodies and about Newton-Euler's equation. Now, this interpretation, it's also very important to understand what's happening. So, you see, the moments are, in a way, what we discussed the other class, right? Moments are the effect of forces. It's very rare that you create a pure moment. And when you do that, it's like a torque, right? So moments are essentially the effect of several forces acting on one rigid body. So you can see the left-hand side is the, let's say, real forces, and the right-hand side is the effective resultants. So this is something that you must have done in statics, right? Quite a lot. Yes? Okay. Now, why do we do that? Why do we go from 4 forces to 1 force and 1 moment? So the reason is this. The resultant force is applied at the center of gravity of your system. And that resultant force is nothing else than the summation of all forces. So that resultant force is going to be equal to the mass times the acceleration of the center of gravity of your rigid body. What is the physical interpretation of Newton's equation? That's Newton's equation, essentially. Well, Newton's equation treats the rigid body as a particle that is positioned at point G, and from the acceleration of that particle, you can get, what can we get from the acceleration of the particle? If we integrated velocity, and if we integrate velocity, position. Newton's law dictates the motion of the particle. That's why we say that, you know, these are the laws of motion from Newton. Very big deal. So the acceleration is what determines the translation, the trajectory of the rigid body. The translation, all right? But rigid bodies can rotate as well. So what is the physical interpretation of Euler equation? Well, it essentially is telling us that the moment, the resultant moment that we have, it's equals to the moment of inertia times the angular acceleration. That equation is telling us everything we need to know about the rotation of a rigid body. So Euler's equation determines the rotation of the rigid body. And that rotation is determined by or is caused by the moments that result from all these forces acting on a rigid body. And we know from, or this is something that maybe you learned here, but you must have heard it before, that any motion of any body can be separated in translation and rotation. Newton-Euler equations are the basis of that. Okay, so this is super important. Does that make sense? Yes? Okay, good. Again, please review these. Don't only take my word for it. Go and take some notes of what the lecture book says. It's important that you learn this. This is very, very important, very deep stuff. Now, one thing that I didn't say, but most of our problems are 2D. So essentially, when we have a 2D problem, due to the fact that the angular acceleration is perpendicular to that 2D bodies, we can always calculate the moment of inertia like that, with that integral. So we don't need to actually take the cross products that are shown there. Now, if anybody wants to do advanced dynamics, orbital dynamics, you know, go and work for Musk or Bezos or one of those guys, or at NASA, then you need to do your cross products because everything is 3D. So now the motions need to be a little bit more complicated. But for us, because we're starting, we keep everything on 2D, so we can always say that we need to be careful because maybe there are exceptions, but in general, we can always say that moments are going to be perpendicular to the plane where we are presented in problems, all right? Okay, so let's do this problem. This one is going to set you up for one of your homework problems. So let me see if I manage to finish it. All right, now this problem also we did before when we did chapter 2. And I don't think because of the pandemic, nobody came to ask me why it was like that, but it's a confusing one because, you know, you're pulling some spool and it's not clear whether when you pull the thing is going to move towards you or is going to move apart from you. Actually, there is a nice animation on this problem on the blog, so if you please look for it. Okay, so we have a spool that has some mass, And then you see, this is the language that we're going to give it. A centroidal radius of gyration about point G, right? Of some magnitude. And then it has two radii, big R and small r. And it's been pulled by a constant force that is applied by an angle, at an angle by a cord. And the cord is wrapped around the spool. Spool rolls without slipping on a rough surface. Okay, that's good. So we're told that this has no slip, that we have a force, and we have a radius of gyration, about point G. Let me use big G here. Yeah. And we're asked to find the angular acceleration of the spool as a function of the angle. Okay? So how many bodies do we have in this problem? Just one, right? Good. This is important because, sometimes cables, it's just one. Okay, so this one body will have some weight applied here, normal force and friction force applied at the point of contact, and then this force that is applied, let's say, at this point at an angle. Any other forces? No, right? That's all. So we are asked to find angular accelerations. We need to use Newton-Euler equations to do that, right? We cannot get them with the other kinetics that we have learned. Okay, so we have one body. Let's calculate the summation of forces in Y. Begin with that one. So that one is negative mg, positive m, plus force, that's sine, right? Sine theta, and this is going to be equals to, in this case it's 0, right? Because the spool is not jumping up. Now, summation of forces in X, we have force cosine theta, friction force. Here, actually, I assume friction to be to the left. But this is an assumption. The equations are going to tell me whether this is true or not. And then this equals to the mass and acceleration of point G in X. And this is our second equation. And now the moments. So where do you guys want to take moments? Do we have choices here? We have G. We always have that one. Any other choice? C, right? So in this case, I'm going to do it with G. But you can try it with C, and you see what's the difference. So G, that gives me then the moment of the friction is, I put friction to the left, so it's negative. Friction force times big R. And then the force. So where is the force applied? Now, I'm going to remove that unknown from you by using vector algebra. Because I'm going to say that this point, let's call it point D, or point F, that makes more sense. I don't know where it is, but I know that the position between F and G is something. And I'm going to do the calculation using the definition of a moment, right? The force times the moment cross the moment arm. Both being vectors. And this is our equation number 3. Now, why do I do that? Because no matter where F is, what I can assume is that if that cable is a cable, it's going to be what to the spool if it's being wrapped around. Not perpendicular. Tangent to the circumference, okay? If it's not tangent, it will be saggy. So if there is tension, the cable needs to be taut. And if it's taut and is wrapped around, it can only wrap around without having some sort of tangle if it's tangent. So the geometry is this. If it's tangent, then it's perpendicular to the position to the radial position. So why did I keep the mathematical definition? And you guys don't need to be afraid of that. You need to use it. Now the way to use it is to remember how it works. By definition, the cross product is the magnitude of the first vector times the magnitude of the second vector times sine of the angle. What did we say the angle was? 90. So sine of 90 is 1. So with this I remove all the complexity of the geometry by using cross products. This is why mathematics are powerful. Okay, and then I was told what my moment of inertia was because I was given the radius of gyration. Okay? This is one of the reasons I actually took moments about G. But if I take moments about C, then I'm not afraid of these because I just need to do this. A big R, sorry, times M, right? Where this guy is kg square M. Okay, so don't be afraid of that. So we have 3 equations, but actually equation number 1 is not really useful to find the angular acceleration. Oh my God, I'm 2 minutes over, sorry. It's not useful. So we only have 2 equations and we have 3 unknowns. So we use kinematics and we have a no-slip condition. So we can use that, right? So to know the acceleration of point G, we use the no-slip condition. We take our cross products and we get these equations over here. And this is what it's important to solve our problem, that we have a relationship between the acceleration in the x direction and the angular acceleration. So we look at the forces in the x direction and we replace, or we relate the forces to the angular acceleration. We find the friction force, and this is very important. The friction is not dictated by this slip model, by slipping or sliding. It's given by the moments equation. Look at that. Okay, we have to do a little bit more of algebra, but then we get this equation over here. What is interesting is the following. It's telling us that depending on how big the angle is, you see, little r is smaller than big R by definition. So cosine of theta needs to make up for that for the angular acceleration to be positive. So let's look again into the geometry. So if the angular acceleration is positive, then this guy is going to move like that. So if I'm pulling like this, if I'm pulling to the right, and the angular acceleration is positive, what's going to happen with that spool? It's going to wrap around. So what do I need for that? I need cosine theta to be big, such that r is small, right? If theta is not big enough, when I pull, this thing is going to unwrap. So I think that that's a very nice result. Okay? All right, everyone. Have a great weekend.